Okay, hello everybody. I hope that everybody is fine. So today I will be talking about flat combining in NUMA-algorithms data structures. I will remind you what flat combining is. I guess on your course, you were presented with this technique, right? On the
Yes.
lecture. So I will come a little bit of overview, and then we will go back to NUMA-algorithms data structure. So I can skip flat combining as fast as I can. Okay. So what is the problem? The problem that typically the data structures are blocking and they're guarded by one lock. For example, for a stack or queue, the most efficient up to 2010, the most efficient approach was to take a lock. However, taking the lock is a huge contention even for locks such as CLH or MCS. Okay, what was the idea? The idea was that instead of inserting into the queue each time as done by CLHLOG, we will have a publication list at which we clear not very often. So the idea is that some of the requests of processors are already in the publication list. That's the main guess here. The requests can be of two types, again here, active and inactive. Inactive, this means that during this iteration, the corresponding process hasn't inserted his request into the list. Okay, how to pass the log? So one process takes the log and goes over the list and apply all the operation requests there. Execute these operations and mark these nodes as inactive. So here is the picture of the flat combining. So we have a publication list, as you can see. We have a head and we have nodes with the request and the age. We need an age to understand when to clean up the node. So what's happening here? So the thread spins on their requests and sometimes try to take a lock. When the thread is successfully taken the lock, it becomes the combiner and go over all publication list and apply these operations there and say that their ages are not so small. So they set the new. And the count here near the lock, it is exactly the current epoch or the current age of the system. Okay, combiner traverses the list and performs scan combine apply. And rarely we perform a cleanup phase if, for example, their phase is I don't know, 0 modulo 100. So each 100th phase, the process goes over the list and remove agely very old requests. So here is how it looks like their operation there. So each request is operation, response, age, the next request in their publication list, and the boolean that marks is it active or not.
One question.
Yeah, sure.
Couldn't thread that is in the list, he's probably sleeping, waiting for response, or waiting. So when we process his operation, can't we notify him so he will delete itself from the list?
Yeah, exactly. This happens. So we can notify this response. Their thread is spinning on the response, to be more precise. So it's spinning not on the request on this request class, and it spins on the response. And when the response is set, then it understands, okay, my operation was applied, so I can get out of my operation. The main difference between the CLHLOGing and thread combining is that you do not remove the node from the queue, from the publication list. Even if you finished your operation, you say, okay, I'm inactive, and I will leave my descriptor there. And
okay.
then once in a while, we remove these old descriptors. But because thread combining is typically done to work on under the high load, you don't have to remove your request object from the publication list at all. So that's the main difference between the locking, like queue locks, and thread combining. Does it make sense, Alexander?
Yes, but you said that under high load, we don't remove this object at all.
Yes.
Won't we meet a problem when there are a lot of objects in this waiting queue?
Yeah, potentially the number of objects will be the number of processors. But if you have a high load system, you're in your CLHLOG, you will have very huge contention on that, exactly on the tail. So when everybody compete to insert a new node, and they're in the tail.
Is a number of objects really limited by number of processors?
Yes.
For example, processor CAM publishes its operation, waits for its completion, then receives response, and then processes it and come again, publish a new operation.
Okay, the tricky thing here is that it doesn't publish a new thing. It takes the same cell, the same response class that is waiting in this publication list, and put the new operation there.
Okay.
So that's a little bit different with CLHQ when you always add a new node in the list. Here you're doing a little bit different. If there is already your request in the publication list, you don't do anything. You just write in that class.
Okay, I understand.
Okay, great. So here is the picture again. So like, yeah, I already told it, I think, how it works. So like it checks for the process checks for the global log. If it is taken, then it spins on the res field to wait for the finish. Then we sometimes check in some number of iterations, we check the global log and the flag active is there. And if the processor takes the global log, it becomes combiner. So when it becomes combiner, it increments their age and execute all active requests with setting their age as count. So and mark them inactive. Okay, what the pretty important thing here also is that it doesn't simply execute their operations there. It can take their operations as the batch and apply it to the sequential data structure. It is pretty interesting that if you have the skip list and you have key operations that you are going to apply, if you apply them together, your total running time will be k plus logarithm n, as far as I remember, instead of k times logarithm n. So we kind of, in batched operation, we can win in the terms of sequential complexity. So it would be faster. So it's like, it's faster by the 2 axes. It's faster because one thread reads all the requests, and then it can load it to himself. And their other part, like they're all in the same cache. And the other part is that you apply them together and you can get benefit from their sequential running time. There. Okay, and Yeah, so we check when the object is in the list, our object. If it is not, then we add it. If like we haven't been in the publication list for a while, we add the new request to the back. Otherwise, you take your object in the request and in the list. Okay, so what can we improve here is that instead of processes to content for the global log, the combiner can choose the next process to be combiner. So we have to compete only for like once, and then if the requests are coming and coming, you will always give their log to the next combiner or to the next process, which obviously improves their total running time because no one should compete for global log after that. Also, if you have the high load, then it's pretty good to use the same process as the combiner for several rounds. So we don't have to change the combiner at all. And if we do this like 5 times, it's a pretty good combiner. Another thing from the B is that we get a little bit of cache friendliness there. If each time the same process goes over all the requests there, it will get less cache invalidations because like some requests already loaded into its memory when it read. Okay, and about like again the queue, and the very important thing here is that everything can be linearized automatically. If you use flat combining, you will have linearization there. Is it clear that we have the simple linearization there?
It seems yes, because we have like explicit locking.
It's not really explicit locking, right? Like we linearize operations in exactly the order which they are applied by the combiner.
Yeah.
So this is their linearization locking. So I guess this was explained in their lecture about flat combining. I'm not going to talk about flat combining anymore here. I will be talking about their like kind of different implementations of it. So the problem with the current approach is that processes spin on the res response while do not perform useful work at all. So like they just spin. But what if we can use it for the future? And here it comes hierarchical, flat combining, and parallel combining. I will be talking about them right now. So what is the idea behind hierarchical flat combining? Okay, as you understood on the high load, there will be a huge competition for the global log. And we want to split this global log into some smaller logs. And so, for example, if we want to implement stack or unfair rendezvous queue, unfair rendezvous queue means that we insert an element like their producers and consumers, and their producer put an element into the queue and some consumer will take afterwards. It is unfair because you're not necessarily perform them in the order they are in the queue. So like not the FIFO queue, so first in, first out, but at some order. You don't care. The advantage of these data structures is that we can pair the requests in any reasonable way. For example, if we have the back of stack operations like push and pops, we can pair push and pops together and then take the rest, which are their operations of one type, and apply them. So we don't have to go to the data structure at any operation. So what we are doing in two-level flat combining, this is hierarchical combining. So at the bottom, we have the normal flat combining, but on their sublists. So as you can see here, we have one combiner node with several requests where, then another combiner node, and then the third combiner node. So each thread knows to which sublist you're working right now. And each thread tries to take not the whole global log, but for the local log, which is for their sublist there. And then when the combiner takes the operation there, it do the pairwise thing with the operations like pop and push. And then it is left with some extra requests. And for that, we have the top part, the top flat combining part is there. It is normal flat combining, but instead of one request, we will have the list of extra requests from their corresponding sublist. And it is fully their normal flat combining there. Instead of applying one request for each node, we apply the list of extra requests. Questions?
So subthreads, their work is to collect all the requests in their sublist, pair matching ones, and excess ones push into the global list. Yes. Yeah,
exactly. Yeah, and then on the top you will have less contention because, like, you, for example, take square root of p to become the combiner node, and the sublist is approximately square root of p, where p is the number of processors. So like you reduce their contention in general. Not there is no such situation where all p processes tries to get one log. Parallel combining is a little bit different thing. It is kind of so like we understand that the processes are sleeping, but we can use these processes to perform something in parallel. So for example, we can implement an interesting version of read-write log. Is that in each data structure, there are read operations and write operations. Write operations will be applied sequentially by combiner, while the read operations can be applied in parallel. So a combiner takes a log and tells all read operations to perform at the same time. And then it goes over write operations. So we get some kind of read-write locking, which works much better. It's a nice effect, but what we know, we're given that combiner takes all the requests together and apply to a data structure. This thing is similar to what we're doing in parallel algorithms. We had batched data structures where you take a batch of requests and apply them onto the data structure. Okay. We had this, for example, when we're talking about pipelining 233, is that we apply the whole batch of operation at the same time. So this is exactly that. They're named parallel batch data structures. Like the most famous one are 233s and the binary search tree. So let us talk about binary search tree a little bit. So parallel batch binary search trees, like right now we're talking about parallel algorithms. So we're given a sorted batch of requests and we want to apply them to their data structure. And this data structure is pretty simple. It will have only the join operation. And here it is explained how to implement any other operation using join, simply one join. This is a data structure, like this is binary search trees like TREEP, red-black tree, AVL tree, all of them can be written in that way. So we have the split operation, split last operation, join two, insert, it is obvious how to do with split and join, delete is also obvious to do with split and join. So their operation, yeah?
Question, what does operation expose do?
What operation expose do? Expose operation is like here, it is taken from the code from the paper, and expose means as pattern matching as in functional languages. So here like T, the tree T is the guy with the root with an element M and two children, left tree and right tree.
Understand.
So this is like just in the terms of functional language representation. So the parallel like insertion works pretty simple. So we take the middle element of the request. So we have the tree T and the request A. We split by the middle element, and we have two, a left tree and the right tree, and then you recursively insert the left batch of the elements and the right bunch of the elements, and then afterwards you join together the left result, the right result, and their element key K there. So it's pretty simple here. I think
the middle element in the inserted elements.
Sorry, the array A is the list of inserted inserted elements. What this was the question, or?
Okay, I understand.
Okay, good. And the very interesting part of that is that the work will be much better if you do this. Like it can be proven. Like you can look at the paper afterwards. Like in the normal binary search tree, you will have m logarithm n if you apply operations one by one. But here it's a little bit different. And the thing is that when m comes closer to n, your work running time will be linear. And to be more concrete even, this is the best running time that we can achieve inserting m elements if we are given only compares. This is kind of the stuff with quicksort, as possibly you remember, or like not quicksort, like the standard data, like standard sort algorithms, is that if you have n elements and you have only compare and only comparison, then your total running time cannot be better than n logarithm n. Here it is the same. The span is pretty trivial. The span is O of logarithm n logarithm m. The problem with this approach that it doesn't really good work into flat parallel combining, because on their concurrent binary search trees, the span is kind of logarithm n. So they're without the contention if you want to insert a new element. So parallel batched binary search tree are not very good to use using flat parallel combining. It works like 5 times smaller, 5 times slower than concurrent binary search trees, unfortunately. Okay.
Question, the span for concurrent binary search trees, is it for inserting one element or m elements?
Yeah, it's if you think about concurrent data structure as the parallel data structure, and you ask all the elements to be inserted, then the span will be logarithm n plus logarithm m. So I mean, we go and we like tell, okay, this guy, please insert into the binary search tree, and this process goes like the normal insert operation. It is not true when the tree is highly contended, but when the number of operations is like 32, or I don't know, like, and the tree is large, they will not clash with each other, and you can simply perform them purely in parallel. That is why you have kind of logarithm and span there. Okay. So what about flat combining? About then, so it's not great as it was mentioned in the original paper. It is really not great. It works a little bit better than the logs. And even sometimes the highly improved Java reentrant log, which is CLHLOG, it works better than handwritten flat combining, it appears. But if, so if, for example, we take a binary heap, like if you want to do the priority queue, I'm talking about exact priority queue, not the relaxed priority queues, where the elements is not taken their smallest one, like we're talking about right now, the exact priority queues, that when you take an element from the queue, it is indeed the smallest one. The binary heap with reentrant log works much better than any other custom exact priority queues. However, if you do parallel combining with binary heap, it will become a little bit better than reentrant log. But for read-write operations, flat combining works much better than read-write log. This is due to the reason how the read-write log is implemented. Like right now, I'm talking about the Java. Typically, it's working for all possible read-write logs. Typically, the read-write logs is implemented using two queues. There is the queue for write operations and the queues of read operations. And since the read operation still has a queue, you will still have a contention to put a read operation to the log. And that's the issue of read-write logs in general. And flat combine, like parallel combining, which is specifically for read-write data structures, it works very good. Okay, where we can see the flat combining to work, it works in logs, of course. And now we will talk about not usual logs, but hierarchical one. So for NUMA. Okay, what is NUMA? NUMA looks approximately like that. So you have, on this picture, you have 4 NUMA nodes. And each NUMA node has 4 cores here. Inside each NUMA node, you will have the separate memory. So right now, when you build their machine, you cannot make, like you can, of course you can have the memory that lies somewhere, the whole memory lies somewhere, and all the nodes are trying to get to that memory. Unfortunately, it is really small. It will work slowly. Unfortunately, because if you have lots of processors, they will try to get to the same memory by the same channel, and it becomes clogged. Instead of that, instead of general common memory, it was proposed to make at each NUMA node its own local memory, so that, for example, cores of the second NUMA node can get to its local memory much faster. And if you need to go to the memory of some other NUMA nodes, you have links in between the nodes. So you can see in the picture there are links. And of course, when you access the not self memory, not from the self NUMA, you will spend much more time than in the local memory. So the best idea right now is that we will try to split the lock into two parts, where you will have the local, like when you have the lock in the local memory of a NUMA node for their corresponding cores, and then the large layer when all other that is stored in their common memory. Okay, so like I want to remind you like the number of logs. So there's a spin log, back-off spin log, ticket log, MCS log, and CLHLOG. MCS and CLHLOG are exactly the guys that we want to work with. Do you know all these algorithms?
If I
Yes,
remember correctly,
What are the questions? What are the algorithms that you don't know?
if I remember correctly, MCS log waits on foreign memory and CLHLOG waits on its own memory.
Vice versa.
Ah, okay.
Vice versa, yeah. So do I need to explain you how MCS and CLH works? I can, because I have slides for that. Should I skip it or should I remind you?
Reminder will be good.
Okay, okay. So MCS log and CLH log works similar way. So you have a node and you have a next element in their queue. So when you add a new element to the back, you just have the log there. And how acquire log works. So we, like the processor wants to store his node there. And you make fetch and store on the tail. So you kind of add it to the queue. And then it waits on his local memory. So like here, while n.locket. So it waits while its predecessor will give it the permission. So here we will have specifically predecessor next is us. So and the release will just have, okay, I will take the next pointer and set its locket field to false. So this is exactly where we release the log. So here we spin on our memory, and then we release it when we give the log to the next guy. We just say there that it is not locked. Okay, CLHLOG is a little bit different. It is vice versa. It is waiting on their predecessor memory. So when we acquire the log, we do the same. We just take fetch and store to the end of the queue, and then we wait on the predecessor Boolean field, which is here suck must wait. When you release, you just set itself its variable as false, and then take the predecessor node for the next iterations. So the very good thing here is that CLHLOG works very good with memory. Indeed, how MCS, to be honest, the logs works. We don't have to generate a node each time. The log can store, can use the same node several times when it gets to the queue. Okay. A little bit of hierarchical CLHLOG. So we will have local logs for each socket, and there is one global log. So what's happening there when the process becomes the first in the local log? It waits for the time to try to take the global log. And then it adds all its requests in the local queue to the global queue. Do I have the picture? Yeah, I have the picture. So you can see here, so we have the local queue and the thread B inserts there. So we have the new node in the local queue, and there were a global queue there. And when their time has come, the thread B decides, okay, I will try, the thread A, which is the head of the queue, it decides, okay, I should add all the requests from my local queue to the global queue. So here is their picture B here. We add all, we simply with one link change, we put their local list to the global list. So we have less contention there. And then you will have the global log where you get the access, gets the permission for the locking. This is exactly like there are still issues with this hierarchical CLHLOG. It still has a huge contention on the local logs. Still have problem. And in 2011, it was proposed to make the local queue and flat combining. And the global queue is implemented by MCS. And this hybrid log worked better than HCLH, than hierarchical CLH, like approximately 2 times better. So yeah, so it looks like that. So we have the local queue, then the guy takes the log of the local queue and tries to insert the whole list into their global MCS log. Okay, in 2012, Dave Dice presented an idea on how to generalize NUMA logs. So instead of having the same log at each level, we can use any possible log on each level depending on the load. So you can have any possible ways to combine these logs together. Okay, so right now we are going to the more recent. With more recent results. So let us talk about compact NUMA-aware log. The issue of hierarchical locking is that you spend too much memory on that, because you have to spend for the local logs like additional memory and for the global logs additional memory. And if you have the large number of processors, you will have a huge overhead. Instead of that, Dave Dice and Alex Cogan, I think they even presented this on the Hydra conference, this algorithm. Instead of local and global logs, we will simply have 2 different queues. So the main, there is the main queue. Each node tries to insert there, and their main idea is that you take, like the first guy in this queue takes the log, and it passes the log not to the next one, but to the next one from that socket. So it's kind of do a little bit trickier here, because like it is better to pass the log to the same socket. I think this is clear intuition for you. And all in between nodes are moved to the secondary queue. Like we just take the whole sub queue and move to the secondary. Okay, when the main queue becomes empty or the timer works, we swap secondary queue with the main queue. We just simply swap them. So the picture is kind of like that. If we look on the data structures, so we have, at first we have the whole main node or main queue with 6 processors or 6 attempts. And the second integer in this picture is their socket number. So the first thread performs its operation and it goes to the right. So like the second guy, its socket is 1. So we skip it. Then we have the socket is 1 here. And we have their 4, the thread 4, which has 0 socket. So this is exactly what we're doing. So we take the threads 2 and 3 to the second queue, the secondary queue, and we are left with the first queue, with the main queue here, like which starts T4, T5, T6. Then we take T4, its socket is 0, it looks on the next node, it is socket 0. And T1 already returns and enters the queue there. So we have, again, T1. Okay, T5 guy sees that, okay, that's not very good. I'm 0 right now, but the timer tells us that please stop doing that. Please stop giving to the secondary queue. So instead of that, we just split, like we just get to the main queue, which is right now T2. And it has all the requests by the first socket.
It looks like here, unlike hierarchical locking, we make all threads to content on a single queue, which is shared between nodes. Is
Yes.
this contention acceptable?
Yeah, so they're not waiting, like these 2 queues are kind of CLH queues, if you want to think about that. So if the guy is leaving their critical section, it tells the next one, you're their leader now. So it is kind of working as the CLH queue there. That it points to the next guy, then you should take the lock. And the next guy is just waits again on the flag, whether it waits on the flag as in the CLHLOG. So it's kind of 2 CLHLOGs, the main queue and the CLH queue. Questions? Did I answer your question?
No, I mean, when you have a hierarchical CLHLOG, there is one global CLHQ, but only, like, for example, if we have 4 NUMA nodes, only 4 threads can contend on this global global head of CLHQ. But here in CNA.
Okay, I understood the question. Yeah, it's, I don't know how really explain it, but it works better. It works better, possibly due to the memory consumption also. Because you don't have to jump a lot in the queues. Okay, something else? Okay, unfortunately I have 5 minutes and I have to leave for a little bit. Then I will be back. let us talk about the data structures for NUMA. So in 2018, there was presented new mask high performance scalable skip list. So what was the idea behind that skip list? The skip list here maintains three different parts. So there is, like, in this skip list, generally you will have kind of two layers. So there is an index layer and there is a low data layer where all the nodes are stored. Instead of that, we will have local index layers, which will be updated, which will be not synchronous. In the terms, we will not store the same index layer at each socket. And then we have the intermediate level layer, which will be again one specific list that will be some subsequence of the data layer. And then to get to the data layer, you just go by the index layer to the intermediate layer. And then from the intermediate layer, you just go to the data layer. So it works very good. It has quite a good speed up on 96 cores. And also I have to know that there are helper threads that synchronize intermediate and data layers together. So the picture looks like that. So we have each socket, as you can see, had three parts. So the topmost index layer, then the intermediate layer, and there is a global data layer which distributed between NUMA nodes. So for example, suppose we're in the second socket and we want to find an element 7. You just go to 0, start from the left, you just go to the 0, go down by 5, then you go to 5, then you go to intermediate layer 5. And then you go to the 7 through the intermediate layer, and the 7 intermediate layer gives you the link to the 7 in the data layer. So for example, how it works, like suppose we want to find a 7 at the NUMA node 1. So we go by 0, we go by 2, and go by 5. And we see intermediate layer has from 5 to 9. So I know that 7 should be somewhere to the right, but I don't know exactly there. So I go at the 5th node here, at the 5th node, and I know the position of the 5th node in the global data layer. So we know the link from this 5 to the 5 that is stored at 3rd socket. And then to get 7, you just go by the data layer and find 7. So that's the main idea, is that index layer and intermediate layer are kind of outdated typically, but they're good enough for us to give the first initial attempt to get the index, to get the correct index. Okay, any questions about skip list right now in UMask?
Seems clear.
Okay, I have to go a little bit. I will make Alexander as host. When I will be back, please, Alexander, give me the rights back.
Okay.
Right. I hope that the cloud will still work. Okay, yeah, it still works. So I will be in like 3 minutes approximately. Okay, I am back. Sorry for this. Everybody's here who wanted to.
Yeah.
Yes.
Great. So we will continue with where I stopped. Then I will have a little bit of. So we will finish with NUMA and we will start with binary search trees, but I will get the water at first. So we start with NUMA skip list. It works well. The question: how to make NUMA algorithms in general? So we are given a random data structure, and we want to do that it works good at NUMA. The standard way to do that is to make a copy in each socket. We have a copy of the data structure at each socket, and we synchronize them using the log. So this is as you can understand, this is kind of what's happening with that's what's happening with distributed systems. Very similar, right? So this is like kind of state machine replication, where the state machines right now are on the socket. So, and at 2017, it was done like black box concurrent data structure. So you are given a data structure and it does it black box for NUMA. So synchronization is done through logs, and the flat combining is used in each log node locally. Okay. So as you can see on the picture, so there are each thread, like each socket, to be more precise. Like at the left is the synchronization part, and the right part. So these are NUMA nodes. So there are two NUMA nodes, and there is local replica on each node. And we store where we are at the shared log right now. So what we're doing, so one guy takes the log of the local NUMA node using flat combining, and it goes to the shared log, and then it goes down until it finds the real end of the log. And then it inserts its operation into the log, and it applies this operation to its local replica. So as an idea, I hope this is quite simple. Is it clear in the terms of the idea?
Yes, something like consensus algorithms.
Yeah, this is exactly. It's not like it's exactly as state machine replication, which is the consensus algorithm. Yeah. That is kind of explains you that NUMA nodes looks like the distributed system. Okay, and finally, for that, I wanted to talk asymmetry aware scalable locking. So this is a little bit different than NUMA locking, but I still put it here because we were talking about locks here. So possibly you know that the new line of processors has 2 or 3 different types of cores. For example, Alder Lake has 2 types of cores. There is small cores and large cores. Large core, the same happens with their M1 processor at MacBook. In MacBooks, they have ARM M1 processors. It also has 2 different types of cores. So there are large cores and the small cores. So if there is nothing very important happening, everything is working on small cores because they take less energy, where the large cores have the best performance, but they cost more. In the new ARM architectures, I think in their Kunpangs one, which are by Huawei, they have 3 different types of cores, like large, medium, and small. So, and this is quite new result from 2022, is that how to do a scalable locking, like which takes these different types of cores and uses it as best as possible. So their idea is that we know which are the large cores and which are small cores. So we have a special queue, like as usual, right? Like CLHLOG. We have a special queue where each large guy want to take the lock, it inserts it to the waiting queue straightforwardly. While the small cores, they add in their special standby competitors. And if it is not added to the queue, it waits some time, and when the time expires, it adds itself to their global queue. So by that, our requests for the lock will be a little bit reordered. So like we want to make like the main idea is that you want to make all big cores always to win, but give some work to their small cores also. And that is how you can do it. So there is a paper like Asymmetry very scalable locking on PIPOP 2022. So this is kind of the latest results. So are there any questions about locking part?
Seems clear.
Okay, good. Whew. Sorry, like it's not very easy to talk this fast because I want to, as I said, I want to add, like, to make 2 talks into one, and each one takes like approximately 1 hour. The binary search trees will be much more complicated, unfortunately, and I have 1 hour. So like if I will not be in time, sorry for that. Okay. Give me please like several minutes. I will like put the water near myself. Okay, my small technical break is over. Everybody's here who wanted to hear what's going on.
Yes.
Oh, it's this, by the way, Nikolai is here, so he heard something about like logs that he is going to implement. That's funny.
Yes.
Okay, let's go with binary search trees then. Like let's start with the interface. So yeah, in this part of the lecture, I will explain how to work with binary search trees in concurrent manner. So binary search tree interface is trivial, so they're insert, remove, and contains, and they're a little bit different from the sequential ones where you just insert and you don't care about the answers. So like it is true if element is not in the binary search tree, otherwise it is false. Remove if the element V is in the binary search tree, then it is true, otherwise it is false. And contains tells true if the element is in their tree. So there are three types of binary search trees, which I hope you're aware of. These are external, partial external, and internal. So partial external binary search trees is the following. So we have the standard binary search tree with keys, and some of the nodes can be marked gray as routing. So what it means that the keys of the data structure are in the white nodes, while the gray nodes are only for the routing information. And as an additional invariant, we will have that each routing node has two children. That's pretty important for our algorithm, because if their node 4 has one child and it is routing, then, for example, 2 is routing also and have one child, and so on and so forth. And you will have the whole chain of elements where all of them are routing. And then each operation will cost very, very high. Instead of that, we should maintain that the routing nodes always have two children. So how the traversal works, we just go simply until we find the leaf, and we maintain three elements like current node, previous node, or previous parent, which is the parent, and gprev, which is their grandparent. So we just do this in their tree. So let's look how insert, like routing, etc. works. So for example, we want to insert a leaf. We go downwards. We find that the current node is null, and we insert 3 at this position. If we want to insert an element which is marked as routing, we just unmark it and it becomes white. Okay, when we remove a vertex with 2 children, it becomes routing. If you remove a vertex with 1 child, for example, here we remove the node 2, so we simply relink the node, the subtree. The hardest case is that we want to remove a leaf. So if the leaf has non-routing parent, so we just remove it and set null. Otherwise, as you can see on the picture at the bottom, we have the routing parent, and we remove 3 with its routing parent 2 at the same time. That is enough to maintain that each routing node has 2 children. So for example, if we remove 3, we cannot leave 2 there because it will be routing and have 1 child. It's not good. Okay, so yeah, and exactly why we need current parent and grandparent is that because on the latest case, we should change the link from the grandparent. So the simplest way to do that is using logs. Also, we can use their deleted field to mark as like the node as logical deleted, which will be physically deleted later. It is the standard trick that you should be aware of from linked list. And there are 2 log policies. Either you lock all the nodes and you lock also the edges, and you have separate locks for the nodes and the edges. So what do you think, which one of the lock policy is better?
Seems like the second one is more flexible, but right now I can't think of many cases where it can be useful.
Okay, so the answer The answer is pretty interesting. Yeah, so like as Alexander said, it is not clear which policy is better. If you have high contention, the second policy is better if you have high contention on the nodes. If you do not have high contention on the nodes, then separate locks per node is enough. Because like separate locks, you take more memory and you have more time to lock everything. But on practice, it appears that on uniform workload, the separate locks are better. Also, we need to remember about deadlocks, the possibility of the deadlocks. So we will take the locks from top to bottom. It is an interesting thing that if you make it from bottom to top, it suddenly will have deadlock. And I found this by myself when I implemented it like I don't know, 5 years ago. That's the funny thing. So then, how should we implement the lock? The lock is typically a spin lock here. But what we add here, we will take spin lock with some condition. And instead of taking the lock and check for the condition to hold, this means that we take the lock not necessarily. Instead of that, at first we check that something hasn't happened, and only then you take a lock and check again. So it works faster. So if you want to take the lock with some check, then you check the condition. If it doesn't hold, then you restart. Otherwise, you take the lock. If the condition isn't hold under the lock, then you unlock it, unlock the node. So it works better.
One question,
yeah.
Do we lock all the paths from the root to our current node, or only we hold the subset of locks? Like for current node, it's parent and grandparent.
Yeah, the subset of locks, yeah.
Okay.
Yeah, I will show right now how it works. So like we take the first example, so we want to insert the leaf. So we read that, okay, here is our predecessor, which is 2. So what we are doing, we log the state of the predecessor and check that it is not deleted. Then we log the right edge and check that it is still null, because this is the case where we insert a leaf, and then you insert the leaf. So the most complicated case is this one with grandparent. So we take from top to bottom. So at first we lock the child of the grandparent and check that the reference still to the node 2. Then we block the state of 2 and check that it is routing and it is not deleted. Then we take the left node, check the reference. Then we take the right node, check the reference, and then we block the leaf. Check it's for not deleted. Why we check for the leaf? Because like someone could already inserted a new element and 3 is no longer a leaf. So we have to check there. And if all these checks are correct, so we have kind of 5 inside blocks taken, we can replace the reference from the grandparent. Okay, so what about asymptotics? Obviously, we didn't have rebalancing, so I guess there is some workload that makes it bad. For example, this is one of the work that Ravil is doing, I guess. To find the bad workload. And we need some balancing. And we can simply add relaxed ABL balancing. This means that we come to the node and we store the heights of its children. And these heights can be outdated, really. And considering these heights, you can rotate the node if necessary. The tricky part is that in the running time, the tree will be only approximately balancing, right? Because our knowledge about the heights of the children can be old. But if we consider the end of the execution, and then we can look on the latest process that goes from the bottom up and rotate everything, it will calculate all the heights correctly. So when the execution is finished, you will have balanced tree. That's the main thing about that. But at the running time, this unfortunately is relaxed one, but like nobody has presented any other balancing algorithms. So the first attempt was done in 2010. Like this is the first concurrent binary search trees. The problem with the previous that it wasn't practical, but they did it very complicated because their get or contain separation works using hand-over-hand validation. So if you remember, possibly, like, do you remember hand-over-hand locking?
Not really.
Okay,
No.
so when you have a list, like I will try to, if you can see me on the picture, like I can try to explain. So you have a linked list, and you wanted to add an element somewhere. There was a hand-over-hand locking approach, is that we take the first guy and the second guy, check if we are there, and then we release the leftmost guy and take the rightmost. Then you release the left guy, take the next one, and so on. And none of the operations, like the operations kind of serialized one after another.
Okay, I remembered.
Okay, so when talking about hand-over-hand validation, it's approximately like that. So what we are doing, we take element by element, you always store the next node, and you do this recursively. And when you get to the child, when you go recursively to a child, you check that nobody changed your parent. And if someone changed, then we get recursion by one level back. Otherwise, we go recursively lower. Yeah, so nobody has affected their edge in between the node and its parent. Deletions and rotations will change the version of the node because the rotation can have a problem there. This is exactly why we need hand-over-hand validation for the contains, because like here is an example. So we are trying to search A. We come to the node C, and then someone did a rotation there. And on the right, you see like someone did a rotation, and we're still waiting at the node C. But contains A is already incorrect because it will never find A there. And this is exactly the case. So we rotate it, and we understand, oh, okay, that's not really good. Something has changed from my parent. So I should recurse one level back. So this is done specifically for that. And there is an additional trick, which I don't think is really important. But when they do rotation, then use a special bit mask to mark the direction of the rotation. So why the direction of the rotation is necessary here? Because, for example, here, if we go to the left and we have the rotation to the right, then contains A will fail. But if we are searching some key in the subtree S, then we don't have to roll back, because on the right, S is still the child of C. So sometimes during the rotation, we don't have to roll back. Okay, the main problem is that get is not weight free, And what is the problem? Yeah, so this is the why we cannot do in weight-free manner, exactly because of this thing with rotation. So the next attempt to partially external binary search tree concurrent was done in 2013, and it did it in a simple way. Instead of rotating the nodes, change the references, we will make the copies of these nodes. So here we will have copies of A, B, and C, which are A prime, B prime, C prime, and set the correct references. Then our traversal will be correct. So our traversal can be weight-free.
And when do we swap the new copies with the previous ones?
At the same, you want to do a rotation of C. You just create all 3 new nodes, replace the references, and then you replace C by B prime here. And then you go back to the top and then possibly rotate something up.
Yeah, I mean that one thread is doing traverse and the other thread is rotating the tree.
Yeah.
So when does the second thread publishes its changes?
No, it's exactly as I told. Like it's made a rotation in the addition in other copies, and it replaces here the link to C with the link to B. So it's just at that moment. So when it did their new nodes is just replace the reference from the top.
So the first thread will traverse the old version of tree.
Yeah, exactly. And that is why it is correct, because we never fail in there, because we never kind of remove the nodes and replace the references. So the guy that does a traversal, it sees their still right version of the tree, but non-rotated. Okay, so what else was proposed in that algorithm? There are main processes, and there is a specific thread daemon. So main processes just perform operations like contains, insertion, deletion, and marking the nodes to be deleted. Daemon, at the same time, it does the structural changes. So main processes do not do like rotations or deletions, and daemon does for that. So it traverses the tree, performs rotation, and maintains the routing invariant on everybody. And since you have these structural changes separated from the operations, this highly simplifies the code. But of course, there is a drawback if the tree is very large and their operations are skewed, that you have some subtree on which you apply a lot of operations, you will have like the bad results of the experiments. I guess it is clear. And one day, like on the large tree, one daemon will, like it traverses the whole tree in some manner. So it's not very fast either. Okay, let's go to internal binary search trees. This is the standard binary search trees, as you remember. So insert still not balanced here. We insert a new element, and you just need to traverse down and insert a leaf. The remove is much more complicated, unfortunately. So if the node has 1 child, then we just replace the reference from the parent. But if we want to remove an element with 2 children, the algorithm is much more complicated. It takes the root, then it has to find the next value in the tree. To get it, you should make one step to the right and all the step to the left. So here is you take 3, you go one step to the right, and then you take steps to the left until you go to the 7 that doesn't have any node on the left. That's how you find their next value. It is obvious to see that 7 here doesn't have the second child, so it doesn't have the left child, because otherwise we will continue going to the left. Then we can simply remove 7 and replace 3 with 7, and that is it. Of course, it can be done very simply here because of all the rotations you have in the future, of like the things that the node can go up at random moments in time, our traversal will not be correct. Because, like, for example, we were looking for 7, and while we were looking for 7, we get to the 97 node, and at the same time 7 is already pop up, and we will not find it. So the simplest version is the log-based version, where you log everybody on the path. Of course, this is slow and inefficient. And plus, we want the tree to be balanced. So, like, this is the issue already of the insert tree. And the solution is pretty simple. In 2014, it was presented. How to find the key in constant time in the next key. Any ideas?
Have
like
something separate list to order them.
Yeah, so we add additional list through all the elements of the tree. Yeah, all additional sorted list. So we will maintain doubly linked list because of some reasons. So how to perform the traverse right now? We need to find an element to remove or to add or something else. We just go, we make a weight-free traversal and get to the leaf. We hope that this leaf is close to our target node, real target node. So we go to the leaf, and then you go to the left or to the right to find their proper position. Yeah, so we find to the left or to the right, to find the proper position there. So double linked list is enough to make all the operations quite simple. So insert and remove are done in straightforward manner, really straightforward manner. And we insert in both directions. We insert in the tree, and we insert into the double linked list. As you can see, this approach is pretty neat, but it works not very well due to additional overheads on the double linked list, unfortunately. However, the interesting fact that the algorithm that is written in the paper is non-linearizable. And 2019, the error was found and fixed, but please do not believe the papers as they is, or their code of the paper as they is, because they that's the good thing that you had on your concurrent data structures course that use link check. Okay, so what about log-free freeze? Up to now, we were talking only about log-based. What log-free? Log-free are much more complicated, to be honest. And we talked previously about partial external and internal binary search trees. They worked faster sequentially, of course, than external. The external tree, they're much simple to implement. So let's look on that. So external BST is the tree that stores the keys only in the leaves. and other nodes inside are routing. So for example, here we want to insert 6. We follow the routing node 4, and we find we should add to the right child. Then you create a special routing node 8, and you add 6 as a child. Remove is also pretty simple. We just remove an element and its routing parent. That's it. So the first attempt for log-free external binary search trees was done by Alan in 2010. Nothing really special here. We just create descriptors for each operation. So in each node, when we try to apply an operation, we put a descriptor there. And then everybody else could come there and help. So for example, here on their picture at the bottom, you have their automaton for the states. So at start, we have clean states. And for example, I want to insert something. I mark as iflag. I use iflag compare and swap. That's to the right, the branch to the right. And I mark their element to be removed. Then I mark, then I store in their child also their descriptor, I flag, and then you replace everything with one cas. The same thing with deletion, but on the left part. Okay, the previous algorithm is a little bit slow because there are too many descriptors, and descriptors are stored in the nodes, which can lead to contention. Instead of that, in 2014, Natarayan and Mittal came up with a way to present the descriptors with only 2 Boolean flags and in the reference to the edges, in the reference to the children. So just 2 bits. We can do that because right now all the references are 64 bits. And the memory right now is not so large. So we can take 2 small, like 2 largest bits for our usage. And this is the trick that only works in C++, I guess. You can do that. So you can represent the descriptors from the Allen work with 2 Boolean flags on edges. And it, of course, makes it better. Right now you have kind of split the descriptors only to the edges instead of the descriptor in the node. Okay, there are more log-free binary search trees. There are, for example, log-free internal trees. Very complicated. What is about log-free balanced binary search trees? The problem is that all their log-free data structures that were before, they are not balanced. It is obviously bad for us. We want them to be balanced. The most obvious way to do that is compare and swap cas n, which is compare and swap on n elements at the same time. I guess you know it because like Roman Yelizar spent like the whole lecture in it. But cas-n doesn't really scale well under contention. So what we can do else? So there is a fast log-free implementation of the binary search trees. This is their paper by Trevor Brown, and it is based on external chromatic binary search tree that has the rotations from top to bottom. So we can do trees not only from bottom up rotations, but we can do also from top to bottom. And to do that, they use lightweight versions of cas-n, which is LLX and SCX. It is like load linked store conditional. I will give you what it is right now, but like these are kind of the versions of cas-n. Okay, I will not talk exactly how linked load store conditional X works, But I will remind you what load linked storing conditional are. So load linked, it reads the register, and story conditional to the register. It checks that nothing has changed in the register from that time. It is a little bit more powerful than CAS because it solves ABA problem. Why so? It is because if the register was set to B and then set to A back, story conditional will know that something has changed in this register. And it will fail. This pair of operations are implemented instead of CAS on several architectures, for example, PowerPC and ARM. However, they support only a weak version. Weak version means that story conditional can fail spontaneously. So it can fail even when everything is fine. You can implement concurrent swap using load linked story conditional. It is pretty trivial. So there is a paper by Anderson and Moyer that explains how to make from one construction to another construction and back. So, and there is an LLSC through CAS. I will not stop here, but there is a way on how to implement LLSC through CAS. But it has much more memory on end processors rather than this simple LLSC. So, for example, like the CAS through LLC has of one additional memory, LLC through CAS has of an additional memory. The good question, for example, how can we implement LLC through CAS with constant time memory consumption? Okay, that's the problem of Java here, that the first binary search trees were implemented for Java because Java has garbage collection and everything was fine. However, you cannot do this bit technique that we can use in C++. So it seems that sorry.
However, everybody.
Sorry. And the only log-free implementation on Java is like the ln and all, which is like on descriptors, and it worked not very good. Personally, I missed some paper, but I hope not. Okay. So all the operations, all the data structures, unfortunately, for binary search trees are hard. Boom, 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 boom.
Can't we use for Java some technique like having a class that stores reference and something like a bitmap?
No, unfortunately, this is already two indirections there. You have indirection on the object, on the node, and on the bitmap. So that's the main problem, is that when you want to change something, you have to get two reference calls. That's the main issue.
Is it really so bad?
Mm-hmm. Yeah, random jumps are really that bad.
Okay.
Okay, what about weight-free binary search trees? So there is one. It is like pretty hard to understand, still not Arayan and Mittal, and they did it on top-down red-black tree. And the idea is something that they store the window that is going down the tree. And when one window overlaps with another, then we help it. Okay, I don't go into details, just know that there is a weight-free binary search tree, which is even their weight-free, but they haven't written it. So like there is no, I think there is no written concurrent weight-free tree. Okay, what about performance? So for Java, there are no, they're mostly normal algorithms are partially external. So if we don't talk about balancing and we have uniform workload, their partial external tree without balancing is the best in comparison to external and internal. And in comparison to the trees with balancing, the one with daemon works the best. If we're talking about C++, the fastest one without the balancing is Natarian and Metal with 2 bits per reference. And for balancing, we have only 1. So some comparison is presented in the paper. And to be honest, BSTs are not really fast. And instead, I would suggest to use their AB tree if you want to. So there is their Trevor Brown's work again, log-free relaxed AB tree.
AB tree is some common case for 2-3 trees.
Yeah, exactly. So this is the common case for a tree, for 2 tree. And it's again, their Brown's work is based on LLX SCX. Luckily, they're a little bit better than compare and swap and CASM. Okay. Then a little bit. So do I have time? Yeah, I have one. I have a little bit of time. So about range queries. So they're like recently, like, I don't know, 3 years ago, everybody understood like we don't care exactly about insertion, removal, and contains. The question was, like in databases, you want to get some aggregate query of the elements which keys lie between low and high. So for example, we want to know the sum of all the elements between low and high, or we want to get all the keys from low and high. One of the first attempts was done by Brown, again, Trevor Brown in 2018. It uses efficient range queries in epoch-based reclamation. So I will talk briefly about memory reclamation in C++. So there is the hazard pointer, which was presented by Michael 2004. The processor just maintain the pointers that they use, and then you want to remove it, you just go over all the processes, check that there is no pointer, nobody uses that pointer, and like remove it. Thread scan is a little more complicated. We have the process that store all the references, even old references, and when the number of old references becomes large, then it takes the global log and tells everybody to do the reclamation. And it does this using the signal to the kernel. So everybody, all other operations will be interrupted at the time, and they had to they have to reclaim the memory. And there is epoch-based reclamation. The idea is pretty simple. So we have the epoch of the operations, and when all the operations of the epoch are finished, then we can remove all the memory that was allocated in this epochs, in that epoch. It's not as trivial as it is, but like we should have 3 epochs, unfortunately, instead of 2. But this is a little bit tricky. I don't want to get into it. The main idea is that you just go and you remove the old epoch. You can see it's in the paper of Brown. There is like paper Deborah, I think it's named. Okay, back to the range queries. If we use the memory reclamation, So we just iterate over the tree and visit all the nodes in the required edge range. We look onto the timestamps. If the timestamps are not correct, then we don't take this node. And if the timestamps are correct, then we know that the node was at that moment. And we visit also limbo lists, which are in the memory, somewhere which are already removed. But you still have the reference to there. And to make it log-free, you can use either DCSS, it is double compare single swap, or CASN. If you want to do an efficient aggregate range queries, where we have, you know that in the balanced trees, you can have range queries, for example, the sum in logarithmic time, if you store at each node the sum of the elements in its subtree. And we come up with an interesting approach, is that in each node, we store the list of operations to apply on the subtree. And to do this log-free, each operation tries to help all the elements at the beginning of the queue. Then you take an element from the queue and push it down to the next level, and then continue helping everybody in the queue until our operation comes up. This is kind of hand-over-hand, log-free hand-over-hand locking. It's just hand-over-hand locking with helping. To do rebalancing, we do amortized rebalancing. Is that if the large number of operations were performed on the subtree, then we can allow us to rebuild it from scratch. So this is kind of the different way of rebalancing the trees. Yeah, and it is simple for the linearization.
When we use this technique with helping, does it look like delayed operations in segment tree?
Yeah, it's exactly like that. It's exactly to do the delayed operations. So it's exactly does the same as the sequential algorithm. Because like it does exactly the same as the sequential algorithm, because like you always push you kind of apply the operations only one by one to the subtrees, and their improvement in the running time you get only from the thing is that kind of if you have uniform workload, your operations will be uniformly spread by the tree. So it has a contention on the top, and then you have smaller contention down the tree. Okay.
Okay.
Questions? Other questions?
For amortized rebalancing, we talk about operations. What operations do we count? Like insert, remove,
insertion, deletion. Yeah. Insertion, deletion. Okay, I will be happy to answer all the questions because we still have time. We have a little bit of time. I know that it's hard that everything I tried to explain it here because I was pretty fast, so we could go it slower, but this is our last lecture. The next time we will have the next 2 times we will have their homeworks presentation. Kind of you will come. I created the queue. I created a list. How its name? List in the spreadsheet. Please write yourself down for the time. Okay. that's it then. Thanks for coming. And
Thanks.
Thanks.
see you
Bye.
next week. Bye.
Goodbye.